Sir. Sir, ready, sir.
Good morning, all. So today I am going to teach the processor design, both data path and controller design. So here the complex digital systems, so we can design data path separately and controller separately. Later we are going to integrate both data path and controller. The simple systems integrated both data path and controller, so together we are going to design. But here, okay, first we plan the data path components, then later we are going to see the controller components. So this is the top-down design approach. Okay? In top-down design approach, we just plan the specifications. Okay, what are the components are required, data path components. We'll identify the data path components. Okay, then we'll develop the data path. Then later we are going to decide and design the controller. Data path components in digital system are mainly like multiplexers, adders, okay, encoders, decoders, even sequential like registers, counters. Okay. They all comes under data path ALU. The controller we are going to design by using FSM, binary state machines, algorithm state machines. Okay. So these are the sequential state machine tools we can use to develop the controller. Okay. So in this processor, the MIPS processor, MIPS is microprocessor, so without interlocked pipeline stages. So MIPS processor, with 32-bit RISC processor, the complete RISC architecture, the total ISTs I am not going to design. So this is customized one. We can develop our own instruction set, small instruction set with small controller we can develop. Okay. Once the program is going to be stored, then next is the registers. I told the number of registers here, 32 registers, each of 32 bit. Then followed by ALU, arithmetic logic unit, then data memory. So here the partial results are data that we are going to be stored in this. So these are the main components are going to be used in this processor designing architecture. So single cycle instruction we are going to develop. That means, so for all instructions will be executed in one cycle, single cycle. For all arithmetic operations or logical operations, load store instructions or jump instructions. So all types of instructions will be executed in one cycle. Right? So then pipeline, execute each instruction multiple step, that will see multi-cycle data. Okay, we can also develop, there is the advantage, disadvantage of single cycle and multi-cycle. Okay, so if you go for multi-cycle, so it takes multiple clock cycles, but clock period will be less. Okay, that efficiently we can run the instructions by using multi-cycle. We can improve the throughput also, but here actually the cycle period is decided by the longest instruction that takes the time. That will decide the clock period. So two types of functional elements in the hardware: elements that operate on data called combination elements, elements that contain data called state or sequential elements. Okay, here the period, the clock period will be decided by the longest path, critical path. So from input to output is the state element. The state element is the propagation delay in the combination logic. Okay, how much the time it takes from the state that input the data it is moving from the output of this flip-flop, the sequential elements, output of this flip-flop to input of this flip-flop, the delay. Okay, that is the critical path delay, the longest path delay, that will decide the clock period of the circuit. The first component is registers. Registers are implemented with array of data. Okay, we can design first registers, 32 registers. Okay, these 32 registers, register means they are flip flops only. Okay, connecting series, the connecting of the flip flops will become the register. We can store that data and we can shift the data. Okay, so here registers are implemented with array of D flip flops. We see this is the register file. The register file we are going to develop. This is required. That is required in the MIPS processor. So in this register file, this contains internally how many registers? 32 registers, R0 to R31. Each of 32 bit. Each of 32 bit, 32 registers. So right. So for this register file, how many inputs are there in this? The inputs are register, read register number 1, read register number 2, and write register and write data. And these are the read data 1, read data. These are the ports of this register file. So these are the register selection inputs. Register selection inputs. One input ports, read register number 1, read register number 2, read and write register. And then write data. So these are the two ports are available. That means simultaneously we can read two registers. Read ports. There are two read ports and one write port. This register file contains two read ports and one write port. That means at a time we can read two registers and we can write into one register. So which register that is indicated by this? The selection input, that is the address of the registers. This is read register number 1, that's the 5 bits. That is the address of the register. Read register number 1 is data read 1. Okay. So which register we are going to read? That address is indicated by this register, read register number 1 and read register number 2, because here one register you are reading. Which register you are going to read? So that address is indicated by this 5 bits. Similarly, register 2 you are going to read. So that register 2 address is indicated by this 5 bits. Okay. Next is write register, because we are writing the one register. So that write register address is indicated by this 5 bits. This is three addresses for register selections. 2 read registers and 1 write register. So that means this register file, it supports 2 read operations and 1 write operation at a time. Two registers we can read, and also at the same time we can also write to one register. Any doubts in this? Okay. Then if you see this, the design simple. Register creation is simple, very large. You can write easily just one line only. Simple, one line. Input assigned to output assigned. At the clock is equal to 1. Or if it is edge, so clock rising edge or falling edge, the input will be assigned to output. That's all. Only one line code only. 32-bit register writing very large creation is simple, very simple. So that we can create like this the 32 registers here. Okay. These 32 registers, we need 2 read ports here to create. How to create read ports? These 32 register outputs are connected to the data selector, multiplexer. Okay, 32 input multiplexer. That we call it as a data selector, because each input is a 32 bit. Understood? This mux is 32 inputs. Okay, 32 inputs. Each input is 32 bit. Okay, each input is 32 bit. Right? So to select this one of the input, how many bits are required here? Multiplexer selection inputs. How many bits are required to select the multiplexer inputs? The 32 is to 1 mux. Okay? So this is 32 is to 1 mux. How many selection inputs are required to select these inputs? 5 bits. Okay? This is the read register number 1. That is the 5 bits here. These 5 bits are used to select any one of these 32 registers. That is the read register address. This is nothing but a read register address that will select one of these 32 registers. Okay? Another read register. This is again second read register data. Again same 32 input, one more mux. One more mux is a second mux, second multiplexer. again 32 bit input, each input is 32 bit, and selection input of the second mux is again 5 bits. This is 5 bits again, so that we can select here by here one register you can select, here you can select another register. Two registers at a time you can select by using these two selection inputs. 5 bits register selection address, here again second register selection address. Okay, so this is about simple. Read ports are implemented with a pair of multiplexers, 5-bit multiplexers for 32-bit registers. Okay, so that means, so 32:1 data selector, 32:1 data selector with 5 bits of the input. The next is write port. How to create a write port? Two read ports are created by using simple multiplexers, two multiplexers. Okay, then write port creation, you have to select one of the register to write. So for that, this is register number, this is 5 to 32. Okay, so this 5 to 32 decoder. So 4 to 16 decoder, 3 to 8 decoder, you know. Similarly, 5 to 32 decoder. You have to use 5 to 32 decoder. 5 inputs, 32 outputs. Okay, so based on these 5 bits input, so one of the output is going to be 1. Decoder output, one of the decoder output is going to be 1. So that one output is connected through AND gate. There are AND gate inputs, AND gate. So then write signal, the write data. Okay, so this is a write data. This is a register selection. Then this is a write signal, one control signal, write signal. This is only 1 bit, write signal. If this bit is 1 and this decoder output is 1, that particular register is going to be selected. Out of these how many registers here? 32 registers. One register only we have to select. We have to select one register to write. So that which register, how do we select this? That based on this number. This number is 5-bit number. This is a 5-bit number. So this will select this decoder output. One of the decoder output is going to be set to 1. Okay. Let us say suppose if we give 0, 0, 0, 1. So which decoder output will be 1? This 1 will be 1. This 1 is going to be 1, logic 1. If this is logic 1, okay, then it's a write signal. When you are writing the data, this write is going to be also 1. Inverted, actually write is low signal, but with inversion we can make it 1. Okay, so this 1, 1, so then AND gate output is 1, then this register will be selected. A clock, a register is going to be selected. Okay, so once this register is selected, then whatever the data that we are going to write, this data, that will be written to that register, the D input. D input is the 32 bit. This D input is 32 bit. 32 bit data we are going to write. Is it clear? So, two read ports and one write port we can create simply by using two multiplexers and one decoder and some gating logic, by using gating logic. Okay, now you see now. So this is a register file, two read ports. Two registers we can read. So by using this address, read register number 1 5 bits, read register number 2 5 bits, and write register. So write register address is this and data is that one. So this is a write data. So two read ports and one write port are created into register file of 32 registers, each are 32 bits. The simple Verilog code only can write simple. These all components I have discussed and shall discuss. Then we fabricate using Verilog. Verilog simple code. Verilog code, you know, Verilog, right? You can create Verilog this register file. You can create these multiplexers and you can connect like this simple. And here also simple decoder. Verilog code you can write and gating log on gate and connect to this register. Register creation is simple. I told already. Just only one line only. Input as a D input. D will be assigned to Q when clock is equal to 1. That's all. That is the register. The D is the 32 bit you have to define array and Q also you have to define 32 bit. Okay. So our first implementation of this will use a single long clock cycle for every instruction. Every instruction begins on 1 up clock or clock 1 up or down the clock edge and ends on the next up or down the clock edge. So one clock cycle. So because we are going to use either rising edge or falling edge, or upper or level triggered, clock high or clock low, you have to use. Okay. Yeah. You see, next is here fetch operation. So that instruction store fetch for PC increment. Okay. What are the components? This is instruction memory. Instruction memory will store the programming instructions. Memory also you can create easily in Verilog, simple Verilog code you can write and you can create this memory, instruction memory. So two-dimensional memory array creation is the memory creation. Okay. So then followed by the program counter. Program counter is what? Program counter is here. It is a counter. It will be counter. Counter can be count the events or pulses. It will increment by 1, increment by 4, or increment to whatever way to design. Okay. Here we are developing the counter. There is one register and one adder. Register and adder. The program counter is implementing through register and adder here. The program counter and one adder is there. You see here, this is the program counter data path. This is the instruction memory. Program counter always indicate the address of the instruction memory. So, okay. So it will indicate the address of the instruction to be executed. So that's why this program counter output is connected to address input of the instruction memory. This program counter, so because here one adder is here, using one adder. The program counter current value, current address. So for example, initially 0. Program counter address is 000. So that 0 is connected here. Then 4. This is a fixed value always. 4. So 0 plus 4. That's the 4. That 4 will be loaded to this PC. So that means program counter always indicate address of the next instruction. Suppose if it is executing the program current instruction at the 0 address. So program counter will indicate the next instruction address. Next instruction address is incremented by 4. Why it is incremented by 4? Why not 1? Huh? Why? Because here each instruction is 32-bit instruction. Each instruction is 32-bit instruction. Fixed size. Okay? So each instruction will be stored in 4 memory locations. Because each memory location, instruction memory location, it will store only 8 bits. Okay? To store one instruction, it requires 4 locations. 0, 1, 2, 3. It will be loaded one instruction. 4, 5, 6, 7, second instruction. So like that, every 4 locations one instruction will be stored there. Because each instruction is 32-bit instruction. So currently it is executing current instruction at the 0th address. The next instruction address is at 4. Because it will increment by 4. So that's why this 4 is there here. 4. It's a constant value. Every time it is going to be incremented by 4. Okay. This way the program counter can be designed simply. One adder is required. What is the size of this adder? What is the size of this adder? 8-bit, 16-bit or 32-bit or 4-bit? Huh? What is the other input? What is the size of this input? This input, how many bits? Huh? What is the size of this address?
32 bit.
Huh?
32 bit.
What is address? Address size? Address already I told, this is always, this registers all, everything is 32-bit. 32-bit address bus, 32-bit data bus. That internal architecture is 32-bit. Okay? So this address is 32-bit. The program counter is also 32-bit. Okay? So it will indicate the 32-bit address. So this input is 32 bits. And here the constant 4 in 32-bit format only. Constant 4 in 32-bit format. Then this adder is 32-bit adder. This is 32-bit adder. Okay? So 32-bit adder is required. That adder will update the address of the instruction every time by 4 and will show the program counter. Program counter is 32-bit. All internal register, whatever I discussed, all are 32-bit registers. Okay? If you see this, you can also verify this. The instruction PC is equal to PC plus 4. PC is program counter. Every time it is going to be incremented by 4. So first, the PC is instruction we are reading from the memory location, indicate the address indicated by the PC. Is the R format instructions data path we are going to see. Here R format data path. So here register file is required because R format instructions it won't require any memory references. Memory it is not going to read or write from the memory. The instruction execution. Okay. So register file, then ALU, then followed by for ALU because here ALU is going to do addition operation, subtraction operation, AND operation, OR operation, compare operation will be done in this ALU one. Okay. So this ALU internally we have to write that add operation logic. Okay. Add operation logic, subtraction operation logic, and all Boolean operation, AND operation, OR operation, compare operation, all the logic will be they have to write in this ALU. Okay. So then by interconnecting this register file to that ALU, so we can able to run all R format instructions or R type of instructions. So right, we see the register is connected to read ports because for any instruction, add instruction, we require the 3 operands. Okay. So we require 3 operands. So for example, add R0, R1, then comma R2. So this we call it as a mnemonic instruction. It's a mnemonic. Okay. Then this one is your operands. We call it the operands. 3 operand instruction. So these are the 2 operands. These are the source operands. These 2 are source operands. Source operand, and this one is your destination operand. Destination operand. Okay. So how it is going to work here? R1 plus R2. The result is stored in R0. So that's why these 2 are source operands. Operand R1 content and R2 content is added, and the result is stored in R0. 3 operands are required. So to execute this add instruction, how many registers we are required? 3 registers. That means 2 registers we have to read. We have to read 2 registers. This is a destination register. That is going to be write. We have to read 2 registers and write 1 register. Okay. So that's why you can see here, these are the 2 registers we are going to read. So that means here R0, R1. R0, R1 registers we are going to read from these 2 read ports. Okay. Then after that is going to be add. After addition, the result is we are going to write again. The result is writing into R0. So right. So then write port. So that means 2 read ports and 1 write port is required by the register type. So at a time we can read and compute the result. After computing the result, then we are going to write into the write register. All these operations, to read operations, then computation operation and writing operation. So all these will be completed in one clock cycle. Okay? So then this instruction. So if you see here, the instruction is 32-bit instruction is required. So this instruction will indicate the address of the three registers. These three registers address is indicated in the instruction template itself. Because here we need to select two registers for reading, one register for writing. But out of that, how many registers in this? Total number of registers, how many are there?
3.
Total number of registers in the register file.
32.
Total number of registers in the register file, how many are there? Not following at all. How many registers we have created first initially? Register file creation. So here we created a register file. Here how many registers? Total number of registers? 32 registers are there, R0 to R31. So this processor internally contains 32 registers, R0 to R31. operation. One, and write again data. We can read also. Where we can use the memory, data memory. So address, this is the address input. Then read data, then write data. Separately is indicated read data, write data. Then write memory signal and read memory signal. So okay, like here read signal, write signal, address, read write data, reading and writing, bidirectional or unidirectional. Okay, so right. So if you see here again, we have to load instruction is reading data from memory, and write instruction is load instruction is reading data from memory, store instruction is writing data from register to memory. So if you see how many read ports are required here, because where this data path is two operations. One is read, okay, then read data from the memory, and writing into register, or write data to memory. Load instruction is reading, the reading data, this is the memory, component, reading data from memory and writing to the register. That's the load instruction. Okay. Store instruction is register value is writing into memory. That is store instruction. Read data and writing to memory. These are the components. Okay. The read connection and the write connection. And the address, because you see the template once again, it will be there in the next slide. If you see this is the template for the instruction for the I format instructions. I format is related to memory reference instructions. Read operation, write operation. So in this case, load word, load RT, offset RS. Two instructions, load and store. So load word, LW load word, or load everything, right? RT, offset RS. So that means here we are reading data from the memory. Okay, the memory address indicated in RS register. RS register indicating the address of the memory. So right. So this is nothing but this RS register. It is a indicating the address of the memory location of the data memory. Okay, and that data and plus if any offset is the offset. Offset means displacement address. Example I give you one example that you can understand also. Okay, LW RT. Then offset is, let us say, some 100. Then RS. Okay. Some RS. Okay. So RS will indicate some address. Okay. Some address, let us say 080 the address of the data memory. Plus this is the offset. Offset address is the displacement. So then this displacement will be added to this. Okay? Added to this. Then we get 0x20001. This is the address. That is the final address of the data. So this is displacement plus base. This is the base address. Base address plus displacement. This is offset, this is displacement. Any 16-bit, 8-bit number it will have the displacement address. Displacement address plus base address. That is the effective address. This is the effective address. This is the final address. So from this address there will be data, and that data is going to be copied and stored into that RT register. Okay? RT is the destination, RS is the source here, but this source register will indicate the address of the data, base address of the data. So offset slash immediate. So offset slash immediate is there. This is in the template. Just go back again. See, this is a 16-bit. 16-bit. 16-bit offset. Offset address is 16-bit. Out of 32-bit, this is the total memory. This will select the memory location. From memory location to selected. Based on this address, memory will be selected. That memory location content going to read to read port, this read data, read port, okay? Read port of the data memory and reading and writing to a register. So which register here? Some register R0, R1 or out of 32 register, one register. So which register I have to write? That is selected to RT. So here RT is an instruction RT. RT. That is RT field, target register. Right? This address will select one of the registers in this. So in that register I am going to write. Okay? Is it clear? Any doubts here? So simple. See, RS and RT. Okay, two registers. One is for base address, other one is target register address. Then that is the immediate address, immediate field, that is offset address. That is sign extended and control bit made to control bit. And then this RS register will be read, RS register, and this will be added. This is the address of the memory. Address of the memory. Then memory location content I am going to read and again write to one of the registers here. The register is, which register is going to write? What is the address of the register? Which register will be written? Register address is indicated by RT field. RT field will indicate the register to be written. This RT field 5 bits will indicate the register to be written. Okay. So here we are not using 3 register fields. Here only the I format instructions are only 2 register field instructions. Instruction template will be like this, okay? Load word R2 comma, so offset address plus the R1. So here the R1 register will indicate the base address of data memory, base address. This is the base address, and this 2000, so that is 2000 is offset address. This is offset address, base address and offset address. So the R1 initially, maybe you can assume R1 contains some address that we have to load initially, base address. Okay, R1 is, let us say, some address. This is R1.
assume R1 is 0x 32-bit address. That's why I am writing 8 digits. The 0x hexadecimal. Okay. So let us say R1 contains this address. So then effective address is equal to the base address, that is R1 plus 2000. R1 content plus the 2000, that is the effective address. Okay. So that is equivalent to R1 content, this is 0x400 plus 2000. Hexadecimal only I am taking, this is also hexadecimal. Okay. So then you will get the address 0x400 200. This is the final, the effective address. This is the address of the data memory. So from this memory, I am reading the data and writing to R2, copying to R2. That is the load instruction. Reading data from memory to register. Load instruction is that. Okay. So here this address of this and address of this register. This is indicated in the instruction template RS field of the instruction template, and this will indicate RT field of the instruction template. Okay. This how many bits? Because this is 5 bits, because here the number of registers are R0 to R31 registers are available in the register file. Total 32 registers. So right, these are the 32 registers are available in the register file. We have created 32 registers. So to select one of the registers, here you have to select R2. To select R2, so because each register we have to assign some address. There is an address, 5 bits address, 0000, that is the address. Next address is 00001, that is R1. So like that it will go up to 111, 5 bits. So these 5 bits will select one of the registers here. So that's why that the 5-bit address, this is the 5-bit address, each register having 5-bit number to select one of the registers here. Okay. RT 5 bits and RS also 5 bits. Okay. So to select this RT should be here, what is the address now? 00010. We got to select R2. So similarly RS selection, because this is some number R1, what is that number? 5-bit number 0001. That's all. Those numbers you have to fill up in the instruction template when you are designing. That is actually, if you write a code like this is the instruction code, automatically the assembler will write that this will be filled with the assembler, the numbers. Okay. So if you see now, is it clear? Any doubt in this load instruction? Load instruction data path. Any questions here? Next is store instruction. This is also memory reference instruction, reverse operation. So that means writing register content to memory location. Writing register content to memory. The same data path it is going to be used. Load instruction, store instruction, data path remains same. If you see, this is the store instruction, store word, we call it a store word. So that means here writing register content, that is RT value, writing to memory. RT value, RT register content I am writing to memory. That memory address, base address is in RS, offset address is indicated by this instruction. So template again this 16-bit offset and RS and RT 2 fields and operational code. Okay. So sign extension, memory address, the base address plus sign extension of this offset, that is 32-bit address, and that 32-bit address, the content of RT, register value will be written to this memory location. Okay. So if you see here that animation, you can understand easily. So here reading the 2 registers and this is the offset address. Okay. Sign extension 32-bit. Then which one you have to read here? This is 32-bit immediate address I am reading. 32-bit immediate address. This is 32-bit immediate address. Okay. Sign extended to 32-bit. The next is we have to add to what? RS. we have to take RS. So then next is RS address, we will select one of the registers here, okay. That register value I am going to read, okay. Yeah, so right, so we are selecting this address RS, this is the RS value, then offset value, it is going to be added, so then that we are going to get the address. This is the address of the memory where you are going to write. So what you are writing? RD2. RD2 is address is indicated by which field of the registers here? RD2. Which field of the instruction template will indicate RD2 register? RT field. RT field indicate the register where you are going to write. Okay? Huh? No. See, RT field is indicate the register, one register. That register content. The register content I am writing to memory. Okay? RT field will indicate one register. You are going to select one register. That register contains the value. That value are writing to memory. This is store instruction is writing to memory. Okay? Clear? Any doubts in this? If you have doubt any, similar operation only. Simply address calculation, then writing a registered value into a memory location. Okay, this is about memory reference instructions. Next is one branch instruction is also there. Branch instruction. The branch instruction is because branch on equal or branch, conditional branch, unconditional branch, two instructions are there. So that means if it is the branch instruction, so if the branch is true, then it has to, next instruction address is it has to go to branch targeted, different address, okay, not sequential address. Branch on equal. Suppose if you write a code like this is the instructions, okay, instructions, this is the code, program code, okay. Suppose this instruction is branch instruction, so branch instruction, branch on equal, otherwise BEQ instruction, branch on equal. The branch on equal instruction, what it will do? So otherwise it is continuously going to execute these instructions, instruction 1, next 2, 3. Here, this instruction, when the processor execute this branch on equal, that means it is going to compare two registers. If two registers are compared, if it is equal, it will skip to some address, some different address. Branch on equal, so then that address may be here. This may be the address. It will branch to this place. Otherwise, if it is not equal, you are comparing two register values. If two register values are equal, it will jump to this address and will execute this code. If it is not equal, it will continue this instruction only. Okay, that means that next instruction address, the PC address, the PC, this is indicated by PC. Program counter will indicate the next instruction address. Okay, if it is not equal, the PC will indicate this address. It will continue these instructions only. If it is equal, the branch is true, the condition is true, then it will jump to this target address. This is a target address. So that means this address to be initialized to PC. The PC should be initialized to this address then. Okay, then it will go to this location. Okay, so that's why here. So one more, the adder is added. See this. This is a register file, and this is the comparator, this is ALU only, same ALU. It is going to compare two registers. So if it is 0 to branch to control logic, that means if it is equal, the two register values are equal, the branch to new address. Okay, otherwise simply, so if it is a new address, that new address is, this is the current address PC plus 4, so from the instruction data path, and new address is indicated from the instruction template. From the instruction template will indicate the new address. So that new address will be added to that current base address of the PC plus 4, and this is the branch target address. Okay. So if you see the instruction template, you can understand that instruction template contains the branch address. This is the branch address. That branch address plus that this is the relative to current address. Current address is indicated by PC plus 4. The relative address, displacement here, the relative, this PC, what is this number? This number is here, PC is indicating some number. What is this number? PC is indicating some 1000, let us say. So 1000, let us say this number is 50. What is the address of this instruction? So PC is 1000, let us say. This number is 50. This number is 50. So that 1000 plus 50, 1050. Okay, that is a relative. This relative or displacement, you call it as a displacement or relative here. Okay, the base is PC here. Base is PC, PC plus displacement, that gives here that destination or target address. Yeah, if you see here, RS and RT offset. Okay, this is the instruction, branch and equal RS RT offset. Okay, that means these two registers are compared. If it is equal, it will go to this offset address, but offset address is not a full address. It is not a complete address. It is only a displacement. But what is the full address? Full address is this offset you have to add to PC. PC will indicate the next instruction address. That is the base. The PC plus 4 plus the sign extension of this offset, that is the full address. So this is the target address. Okay. Otherwise simply, so if these two are equal, then it will go to target address. The target address is computed by adding this offset to PC plus 4. This is the target address. Okay. So if it is not equal, what is the address? PC plus 4 only. Simply PC plus 4 is the next address. Okay. Yeah. If you see this instruction, so taking the two registers, okay, then two registers will be read. Two registers are going to be read based on these numbers. Okay, and this offset address, this is offset address going here. First these two registers will be read and compared. Okay, and if it is equal, 0 flag is going to be set. Then that immediate address, that is the offset address number, this is sign extended to 32-bit. Then again shift left, this shift left by 2 to increase the range of that address. To increase the range of that address, and then PC plus 4, and these two will be added. Okay, then that is the target address. Branch will take place to this address. This address. So that means the branch addition, one more adder is required here. Extra one more adder is added. This adder is, what is this? This is ALU, but this one is simple adder, just only adder for computing the branch address. Extra adder, 32-bit adder is to be added. So if you see now, this is the total data path, single cycle. In this, it supports R format instructions and memory reference instruction, data format, load and store instructions will be executed on this data path. Okay. So here this is a register file, this is ALU, and this is a data memory, and some multiplexer we have included. Two multiplexers are there. So to support, okay, to support for both R format as well as the I format instructions will be executed on this data path. Both R format as well as I format. You can verify also. So first we will verify with R format instruction. R format is add instruction, 3 operand instructions. Okay. What is the data path components is used for executing of this instruction? If you see this, so same. So this is the data path component, it is going to be used for executing of this R format instruction. So that means here reading two registers RS and RT, okay, but one multiplexer is there, okay. So we are bypassing that immediate address, only taking the two registers RD and then adding. After adding, again multiplexer here, okay, then the result is going to write to register. So now this highlighted path is the R format instruction template. R format instruction will be executed in this path, all R format, add operation, okay, subtraction operation, AND operation, OR operation, okay, that will be executed in this data path, okay. Next is R format instruction, load word, let us say. So how this will be executed on this path? So because here in this contains offset address, this will take offset address, sign extended, and see it is a bypass here, multiplexer RD2, not there, not reading RD2, okay. So this address is now offset address, 32-bit offset address, then base address, this is base address RS is going to be read, and these two will be added, that is the result of the address. Then address is selected, then the address memory location content is going to be read from this, the data is going to be read, and that read register again it will return to the memory, the register file, reading data from the memory to register. This is the data path for load instruction. Data path components will follow this highlighted path for load instruction. Any doubt in this? So why we added multiplexer here? The one multiplexer, here one multiplexer, two multiplexer added to support R format as well as I format, okay. R format as well as I format instruction will be executed here. Next is stored word. Stored word is same, see. Yeah, stored word is similar, RS and RT, this offset and RS, that will be added, okay. So here we are, the blue color one is offset, this offset address, then RS is read here, and that will be added, that gives the address of the memory. Then we have to write register value, RT value, we have to write to this memory, okay. That RT address is indicated here, one of the registers here, RT address, and then we are reading that RT value and writing to memory, fine. So just by including two multiplexers, so it can support, so all 5 instructions, that is AND operation, OR operation, all R format instructions as well as the I format instructions will be executed in this data path. Next is instruction fetch included. Just now the previous we are not added the memory, instruction memory is not there in this. Okay, assume that instruction, this is the instruction you are coming from somewhere. So then you can add the instruction memory. This is the instruction memory. The instruction memory, program counter, incrementer. Instruction memory, program counter, incrementer. This is the register file. Then this is the data memory. This is the ALU, and these are the multiplexers. This is adding instruction fetch. Okay. The next is one more adder is added here. One more extra adder. This adder is, with the help of this adder, we can run J format instructions. Branch on equal instruction, that branch on equal instruction also, it can be executed with the help of this instruction, this extra logic. So this adder, the shifter, one shifter and one adder, one multiplexer, extra adding these 3 components to the data path, we can able to execute R format, I format, J format instructions. Okay. Okay. Now see, this is add instruction first. Add instruction. So for add instruction, program counter should be incremented by 4. Okay. See the program counter value will be added by 4 and bypassing this path. This path is not required for simple addition instructions or R format and I format instruction. This path is bypassed. So see, this path is going through multiplexer and incrementing and writing to PC. The green path is, what is the green path indicates? Address incrementing. Okay, and this one is, this path is for reading instruction from the instruction memory, and this is for reading 2 operands from the register file and adding and the result is writing back to register. Okay. Next is load word, the load word path. Load word, okay, same. So the green is incrementing of the PC, and this one is reading instruction and offset address, computing the offset address, then reading data from the memory and writing to a register. Load word instruction. Then store word. This is a stored word, again same similar. So offset address calculation, total address calculation, and writing register value to a memory. So next is branch unequal. Here just concentrate. Branch unequal. Branch unequal R1 R2 offset. Branch unequal R1 R2 means it will compare R1 and R2. If it is equal, then we will jump to the address indicated by the offset. Offset is not complete address, but this offset plus PC, that is the target address or branch address. It will branch to that address. Okay. Now if you see, first reading 2 registers from the instruction, it is reading 2 registers. So after reading, these 2 registers will be compared here. After comparing, if it is equal, suppose if it is equal, then branch to target address. If it is not equal, it will come. It will okay. First we will see if it is this one is not equal condition. Simply PC plus 4 is added to this. Okay, then it will be loaded into this PC. If it is equal condition, that PC plus 4 plus this offset address. This is offset address, no? This offset address will go here and will be incremented or multiplied by 4. That is 32-bit extension multiplied by 4. That is a increment, increasing the range of that offset range. Offset range increasing purpose, this one. Then added this, then that is the target address. Okay, this address is copied to PC. So 2 conditions here. Branch, if it is equal, not equal. If it is equal, what is the target address? Target address is adding these 2. Adding these 2. That is the offset address. This is the offset address you are reading. Offset address plus PC plus 4. This is the PC plus 4 plus this offset address. That is the branch target address. That branch target address will be returned to PC. Right. Once you load the PC, means that will indicate the address of the instruction to be executed. Okay. If it is a not equal, suppose, if it is not equal, this is not a 0, then in that case, so this address will not be there. So simply only this address only, it will increment and will write into the 4. This path will be bypassed. So because here multiplexer is the multiplexer. The multiplexer, what it will do, it will take directly this address. So here it will go from this address, and that address will be copied to PC. Okay. So this is about the data path creation. Complete data path is created for all the 3 formats of instructions. Next is control format, control designing. So any questions from here? So this is the data path, total data path of the processor. Next is a controller design. The controller, so because here what are the control signals? If you see, control signals are, so these are all control signals. Here source selection, the operation, because three control pins are there. So this will select 8 different operations of ALU: addition, subtraction, R operation, AND operation, shift operation, load operation, store operation. This will be selected by these 3 bits. And this is source selection, the multiplexer, whether you have to take this input or this input. Again one more selection here. And memory write, memory read, and yeah, that's all. Then register write. Register write, ALE source, operation, PC source, memory registered, memory to register, memory write, memory read. These are all control signals. Okay. These control signals are generated through the controller. Okay. So we have to design the controller for that. So control unit generates ALU control input, write enable, possibly read write also, signals for each storage element, and selector controls for each multiplexer. Okay. So plan to control ALU, main control sends 2-bit ALU OP control field to the ALU control. Based on ALU OP and functional field of instruction, the ALU control generates, so 3-bit ALU control field. So here the controller we are generating, but this is a very simple ALU, simple processor, two level controllers here. So this is two level, one level, this is second level, two level main controller and sub controller. Main controller followed by sub controller. Main controller is going to generate some control signals, encoded signals, and these encoded signals plus instruction field. Instruction field 6 bits are there. If you see the template of the instruction, is there? Yeah. So here functional field 5 bits, 6 bits. This is the operational code, functional field. This shifting operation we are not using. This amount we are not using. We are putting all zeros only. This is complete zeros. These 3 fields we are using, and opcode field also we are using, and as well as functional field we are using. Okay. The functional field is 6 bits. Okay, that functional field 6 bit, instruction functional field. Functional field, what type of operation? Addition operation, because you have classified that instructions, I format, R format, J format. If for example I format, it is a load instruction or store instruction. Okay, similarly if it is R format, addition or subtraction or AND operation, that will be decided by this functional field. So main controller input, what is the main controller input? Main controller plan to control ALU, main control sends 2-bit ALU OP control field to the ALU control based on ALU OP. So what is the main control input? Main controller input is operational control, operational field, opcode. Yeah. So here opcode. This input of this main control is opcode. Opcode field is the instruction. If you see, this is the opcode field. This is how many bits? 26, 5 bits, 6 bits. So these 6 bits are input to the main controller. These 6 bits are input to the lower level, next level controller, second level controller. Okay. Yeah. So this is main controller, 6 bits operational code, 6 bits. Then from that it is going to generate 2 bits ALUOP, 2 bits. And these 2 bits ALUOP and as well as instruction 6 bits will generate the ALU control input. ALU control input, if you see, so here, yeah, if you see, this is the ALU control input, 3 bits. These 3 bits will indicate the what type of ALU, what type of operation it has to perform, that ALU control. That is the 3 bits. Yeah, if you see functional field, ALU control field 3 bits, 00 for AND operation, 001 OR, 010 add. This we can decide ourselves because you are designing yourself completely. If you develop your own assembler, if you write your own assembler, this is your choice only completely. You can select this. Which bits per what? You can select yourself. Okay. Then add for loads and stores. This 00 because here ALU OP is a 2 bits. These 2 bits based on what? So add for loads and stores 00. That means we are load operation store. Instruction address calculation. Okay, so that is load word, store word, add operation, ALUOP. Here the 2 bits are 00. So then normal, then one more is branch sub. The branch and equal. Branch and equal instruction we have seen. Branch and equal means it has to compare the two registers. What is the compare operation means? Comparing means subtraction only. 2 register subtraction is the compare operation. So that this subtraction is normal subtraction or the subtraction for branch instruction. Okay, if it is subtraction for branch instruction it is 01. So here 00 for add operation, but that add is not normal add. That is address calculation for load and store. And 01 for subtraction, but this subtraction is not normal subtraction, arithmetic subtraction. This is for branch instruction subtraction. Then other operations like addition operation, subtraction. This is a normal arithmetic operations, addition, subtraction, R type of instructions. All R type of instructions, the 1 0. So that is the encoding operation from the main controller to next lower level controller. This OP 2 bits we are generating 0 0 0 1 1 0, only 3 bits. Okay, 0 0 for addition, 0 1 is for subtraction, and 1 0 for R format instructions. That based on main controller. So by these 2 bits and this instruction field 6 bits, then we will generate this ALU control field 3 bits. That 3 bits are this. These are the 3 bits. These 3 bits are this: 0 0 for AND, 0 0 1 R, 0 1 0 add, 0 1 1 0 subtraction, 1 1 1 is set less than. It's clear? So then simply if you know this, then you can write the truth table. Truth table, input output table you have to write. So this is the truth table format. So load word, stored word, ALU OP. Just now you have seen load word, stored word, add operation ALU OP 0 0. Branch unequal subtraction 0 1. Remaining R type of instruction 1 0. This is ALU OP output, main controller output. So then instruction operation, the functional field, this is a load word, stored word, branch unequal, add, subtraction, AND operation, OR operation, set on less. So this is the functional field, 6 bits functional field. So right, this is for R format, there I don't care, functional field. So because here addition operation, there is no opcode for this function operation, because load word instruction internal operation. That add operation is load word and store word internal operation. Similarly, this also subtraction we are doing, but that subtraction is branch instruction internal operation. That's why there is no separate functional field, they don't care. But these are the functional field for R format instructions all, okay. And these are the desired ALU action and ALU control, just ALU control. So these 3 bits you have to generate, 0 1 0 0 1 0, because same addition, subtraction is 1 1 0, and again see 0 1 0 addition only, 0 1 0, because ALU, no, ALU based on that ALU control input, it has to do either addition or subtraction or R operation or AND operation. That's why if you see this here, this add 0 1 0, this add also 0 1 0, subtraction 0 1 1 0 1 1 0, same subtraction, same operation. So then AND operation, R operation, set on less. Okay. So ALU OP 2 bits, functional field 6 bits, the operation is 3 bits. This is the output. This is the output. These are the inputs. These 2 are the inputs. If you know the inputs and outputs, truth table, so you can design a controller. Simple combination logic you can design. You are not designing with the, because state machines we are not going for state machines. Why we are not going for state machine? Because each instruction is executed in only one clock cycle. Single clock cycle only we are designing. If it is designing with single clock cycle, if it is a multi-clock cycle, then you have to go for state machine design. Okay. So, but because each instruction is going to be executed in single clock cycle, so then just controller is simple combination. Okay. So these are the control signals, all control signals, 9 control signals. So these 9 control signals operations is described in this table. 9 control signals where we have to do, what purpose this. Okay. So then this is the main controller. I told you just now the main controller. This is the main controller. Okay. So from this it is generating ALU OP 2 bits. This is ALU 2P, ALU OP 2 bits. Then instruction field, the 6 bits of the instruction field, and ALU OP, this is another controller, ALU controller. This will generate 3 bits ALU controller. This is the main controller, sub controller, the 2-level controlling. So right, so then you can write all the bits, and also you can develop simple combination logic. Yeah, we can. This is for verification. So because truth table is written here, R format instruction, what are the control signal status, whether it is 1 or 0, a load word and stored word and branch unequal. So you can verify this. Okay, this is for R type of instructions, R format. All R format instructions, control signal should be like this. Okay, R format instructions, if you see, this PC source should be bypassed because this is only PC plus 4 incrementing, this should be 0, and destination here, so because 2 registers, okay, register destination is the 2 registers or type of 3 registers as RD, RT, RS, RD should be, this should be 1, RD selection, so that should be 1, and ALE source here again 0 input you are selecting, memory read operation or memory write operation, because this is a R format, no, not required memory read, memory write, bypassing this memory through multiplexer, multiplexer selection 0. These are the control signals for R format. Similarly, control signals for load word, the load word control signals, okay, then stored word control signals, okay, this is the stored word 0, 1, 0 is selected, okay. Then next coming to branch and equal. Yeah, branch and equal, just tell me, see branch and equal how it is happening here. Branch and equal, so because subtraction, the 0 flag is equal to 1, then destination address is computed, the destination address is added with the PC plus 4, this address is a branch and equal, 1 if 0 is equal to 1, this is 1, the 1 or 0. So because here this is 1 only, this is 1 and 0, this is 1 and this is 0 input is equal to 0, then this address will be added. Control signals shown, control signals for branch and equal instruction. Okay, this is for data path with control 3, one more controller is added here, one more component is added, extra component, one more component. Will follow or not, we will see. So this is one more component, extra one more multiplexer is added, okay. This to support jump instruction, unconditional jump instruction. Conditional jump instruction we have seen, but unconditional jump instruction, but to support that unconditional jump instruction, so this logic is extra logic, this branch and one AND gate, okay, this AND gate followed by this one multiplexer, extra multiplexer is added, unconditional jump instruction. So that will support the unconditional jump instruction. So if you see the unconditional jump instruction template, you can understand, okay. So first template is there or not, we will see. Okay, we have to go back otherwise, so long. So because the unconditional jump instruction template is 24-bit address. Yeah. If you see this, then PC address, this is a 26 bits. 26 bits. Immediate address is 26-bit address. That 26-bit address again it will be converted into concatenated with the PC address also. Concatenated with the PC address, then it makes 26 to 28. No, not concatenation. Before concatenation is so 28 bits, and after concatenation with the PC 4 bits, 28, 29, 30, 31, 4 bits. Concatenated these 4 bits with this 28 bit, then that becomes 32 bit. So jump address is indicated in the instruction template is 26 bits. Jump instruction. The template, instruction template immediate address is 26 bits. These 26 bits are converted into 28 bits by shifting shift left 28. After 28 then concatenated 4 bits, so then converted into 32 bit. This 32 bit address is the jump address, unconditional jump address, okay. That address is loaded into PC. Okay, this is read to source registers in the register file. Okay. Okay, we will see the controller. So this is the logic for the controller operation, ALU control logic. Okay. So this ALU OP, and this is for functional instruction, then ALU operation. This is a 3 bits operation. 3 bits you are generating through this. And final controller, if you see the main controller, this is the main controller. All control signals are generated. So by using this controller, this OP bits, operational code 6 bits. This operational field from where? Instruction template only. Instruction template upper 6 bits of the instruction. Out of 32 bit, the last 6 bits are these bits, that operation field. And plus this will, from that it is going to be generated R format, road bus, toad road, branch and equal. So corresponding control signals, these control signals will be generated. So in this ALU OP again, so from this ALU OP signals, two signals are generated. From the main controller we are generating 2 ALU OP signals. That 2 ALU OP signals are using here ALU OP 2 bits. That 2 bits plus functional bits 6 bits and generating ALU control field 3 bits here. These are 3 bits. This is 2 level control. This is a main controller. The previous one is main controller. This is a sub controller. Okay. This is the main controller. These are all inputs. This is the outputs from the truth table. From that you can develop this simple logic controller. Okay. Any questions here? Any doubts? Any questions? Simple Boolean equations only. This is simple Boolean equations you have tried, you will get a gate. So assuming fixed period clock, every instruction data path uses 1 clock cycle, CPI is equal to 1. CPI is the clocks per instruction. Okay. Right. Cycle time determined by the length of the longest instruction path, CPI. Okay. CPI is 1 because here every instruction is executed in single cycle. We are designed for single cycle data path only. Single cycle data path, not multi-cycle. So every instruction is going to be executed in single cycle. That's why the CPI is equal to 1. Okay. So cycle time determines the length of the longest instruction path, load. So that is the load instruction. It is only, it is taking so longest data path. If you see, so that will decide the clock period. Okay. So then for all instructions it has to follow that clock period only. Okay. So unnecessary other instruction like R format instructions, it may take less time for execution, but because of this constraint, the this load word instruction constraint, all instructions has to follow only that clock cycle period. Okay. But several instructions could run in a shorter clock cycle, the waste of time. Okay. So consider if we have a more complicated instruction like floating point, the resource are used more than once in the same cycle needed to be duplicated, the waste of hardware and chip area. So these are the some of the differences between fixed period clock versus variable period clock in a single cycle implement. Okay, but variable clock designing is difficult. Okay, in the same processor, if you are designing for variable clock, so some instructions operating with 1 clock frequency and other instructions are executing with some different instructions, different clock period, it is difficult, complex logic. Okay. So here consider a machine with an additional floating point unit, assume a functional unit delays as follows. Okay, this is some calculations are there. Okay. So multi-cycle is the best approach to efficiently utilize the clock period for the all instruction execution, multi-cycle approach. Okay. The multi-cycle break up the instruction into steps, each step takes 1 clock cycle. Okay. And balance the amount of work to be done each cycle so that they are about equal, and restrict each cycle to use most once each major function unit so that such unit do not have to be replicated. Functional units can be shared between the different cycles with 1 instruction. Okay. So between the steps of cycle, at the end of the 1 cycle, store data to be used in later cycle of the same instruction. So need to be introduced additional internal registers for this purpose, programmer visible, invisible registers. Data to be used in a later instructions are stored in a programmer visible state element, the register file or PC and memory. So, by adding some extra components, extra registers, okay, but most of the functional units, the duplication of the functional units can be eliminated here. Okay, it will become very simple if you see the this is the single cycle data path whatever you have designed, but this one is a multi-cycle data path. Okay, so the components are, we can reuse the components. We need not require the multiple components. See, one adder, here one adder is ALU. So two extra adders are there. One adder for address calculation. This is for jump address calculation. This is for actual ALU. So, but that can be eliminated. Some of the components can be, we can remove that and we can put only one ALU. That ALU, this ALU itself, it can use for solve these address calculations as well as arithmetic calculations in multi-cycle operations. Okay, that is the advantage of the multi-cycle data path approach compared to single cycle data path approach. Okay, so duplications of the components can be eliminated and efficiently utilize all the components. All the components, all instructions will be executed in equal length of clock cycle. Okay, so because the instruction execution is the breakdown into small components, and each operation will be done in one cycle. So, for example, in that case, one instruction may take 3 clock cycles, other instruction may take so more clock cycles, 4 clock cycles, 5 clock cycles. So, number of clock cycles will vary. Okay, right. So, this is the way we can split that instruction: fetch instruction, decode, execution memory, access, R type of instruction, memory read or write, memory read completion, write back. So, like this we can split that instruction execution into the various blocks, and each operation can be executed in one cycle. Okay, so that we can reduce the clock period. We can reduce the clock period. So, we can efficiently use the clock. We can increase the frequency of operation here because we are reducing the clock period. Okay, this I am not going to cover, this multi-cycle approach. Okay, because our valedictory is scheduled 12:15. Okay, so from 12:15 to 1 o'clock we are going to close this session. Okay, valedictory will be planned in 12:15. Right. Okay, if you have any questions, just ask me. Then otherwise I will close.
I request dignitaries on the dais to stand for Vande Mataram song.
Vande Mataram, Vande Mataram, Sujalam Sukhalam, Malayaj Sheetalam, Sasya Syamalam Mataram, Vande Mataram, Shubhrajyotsna Pulakitayamini, Pullakusumita Drumadala Shobhini, Suhasini Sumadhura Bhashini, Sukhadam Varadam Mataram, Vande Mataram, Vande Mataram.
Now I invite Professor P. Muralidhar sir to speak the summary of the GAN course.
Good afternoon all. respected Dean, IRA, Professor B. S. Srinivasarao sir, Srinivasarao garu, respected HOD, Dr. D. Vakula madam, Professor Vakula madam, and my dear colleagues and your participants. So it's my privilege to summarize this 10-day the Gian course that happened from 8th February to 17th February. The Professor Bhaskar Chaube is from Gian University, Germany. He's visited our campus. He has conducted this Gian course, and because of some Gian. So because of some urgency, he has completed whatever the courses we allocated to him. He has completed within 8 days. That total quota of he's actually handled 24 hours of lecture hours and 8 hours of tutorials. Total 32 hours of lecture schedule he has completed, and he has left on Friday. And the rest, the 2 days, last 2 days, that is Saturday, Sunday, and Monday, these 3 days, myself as well as P. Srihar Rao sir handled. Srihar Rao sir, myself handled 6 hours each, okay, lecture hours as well as the tutorials. So in this total, the planned course is total 44 hours. So out of that 44 hours, 5 tutorials, each of 2 hours each, and the rest is lecture hours. The Bhaskar has covered actually starting from the basic introduction to robotic head, starting from the basic introduction, starting robotic head, what is the robotic head, and what are the internal components, what is the history behind that robotic head, and what is the future robotic head he has covered in the first day itself. Then later he has covered some basic history related to imaging, different types of imaging systems that are exist over the decades, and what are the latest imaging system, and that history also, yes, they covered, and what is the future imaging system, it's going to, how it is going to be happen. So in robots, that is covered in the first few lectures. Then at the same time, the lab tutorial also, like basic image sensor designing, imaging sensor designing is explained, and theoretically complete semiconductor chip image sensor chip designing. So is thoroughly is actually demonstrated in the lab. Okay, in the Cadence software, the 1 megapixel, each and every one you might have already simulated 1 pixel image sensor. Then later you have created 1 megapixel imaging system, image sensor, 1 megapixel image sensor. So you have developed and simulated and verified in the laboratory by using Cadence software. So that is a great thing he has done, because but I too, we actually am not aware of how that imaging sensor can be designed by using Cadence. Okay, just by using 3 transistors, he has developed that imaging sensor, and then cascading that 1 megapixel imaging chip created just within few minutes in the Cadence laboratory. Then later he has covered many advanced topics of the robotic head, like vision systems through imaging, then later audio, and then sensing, like sensing circuitry, signal conditioning, sensing circuitry, like a temperature sensing, as well as the chemical sensing, then gas sensing, and pH sensing. With the pH sensor, simply a simple circuit he has developed, the semiconductor circuit he has demonstrated in the classroom. So that pH sensor we can use for multiple applications. Even diabetic detection also we can on-chip, all these on-chip designing only. All these sensors, chemical sensor, gas sensor, pH sensor, skin temperature sensor, these are all on-chip sensors, semiconductor on-chip sensors. They are designed with different techniques, but in semiconductor on-chip sensor designing, that is useful in a robotic head. So because in robotic head, the sensing has to be automatically, it has to occur in the future intelligent robo. So for that is covered, and also some computing, like neural networks part also. Basic neural networks, okay? Basic neural networks, how it is going to be computed, how it is going to be classified. in the real time operations, because here sensing and the processing should be happen in the same chip, sensing and processing, and final output it has to be generated in the same chip. So that portion is actually is covered through the neural network portion. Then so myself and Srihar Rao, I covered the first lecture is on related to FPGAs, FPGA internal architectures, how the FPGAs are programmed. Okay, so actual circuit how to be mapped onto the FPGA. So that portion I covered myself last on Saturday, and also one laboratory session also handled the implemented, how to implement the code, whatever you have developed the FPGA code, and implementing on the FPGA, and how to test that implemented code with the help of IPs like VIO IP, okay, and also ILE IP. VIO and ILE IP is how to test the logic that I covered in the EDA lab. Then today and then later P. Srihari Rao sir, so you might have attended that class. That is happened yesterday. Yesterday it took almost nearly 6 to 8 hours continuous. Morning 4 hours and afternoon 4 hours he start. The total complete what is VLSI, basic CMOS VLSI is it is excellently presented. So P. Srihari Rao sir. Then today my last lecture today is the processor designing. The processor designing, single cycle MIPS processor designing, just explained, and the data path and controller designing. You might have enjoyed and might have learned many new things. Okay, I am actually fully confident about the course. Okay, I am fully happy that because the people that need that they want to learn. Some people are with interest. They attended this course and learned some, at least some the basics, few basics you have understood from this course. If you learn from this course, that is the course may be, the purpose of this course is successful. That's what we thought of. Okay, so sir, actually the participant is concerned 15 students from the Kakatiya University is attended, and 2 students from the JNTU Jagityala and JNTU not Mantini, Sultanpur, sir, Sultanpur, and 2 participants actually from the industry, defense labs, and one participant from the private industry, and Vagdevi lecturer, 2 Vagdevi colleges here. So private engineering colleges, 4 participants are there, and 2 participants from Vasavi Engineering College and VNR Vigyan Jyoti, and then Mallared Engineering College. The 3 participants from the these are the participants from the various outside institutions, and also some participants from the industry also there, so private industries, and the remaining rest of the participants from our scholars also attended this course. Thank you, sir.
I request Dean IRAA Professor S. Srinivas sir to speak some words. To give feedback.
So participants can
I-
give your feedback. Maybe those who attend regularly for our sessions are maybe okay, no problem. Anyone?
Hello. It's my privilege to honor the dignitaries on the dais and off the dais. Good morning to all. Good afternoon. So before going to give my feedback, first of all, so this 10 days Gian workshop was very useful for me. I learned how to design a 1 megapixel camera. Professor Bhaskar Chobe sir explained nicely, point to point, each and everything. Before coming to this workshop. Actually, I thought that robotic means automation things will be happens. I thought, but sir was explained. Actually, it is about camera only. So he framed everything, each and every topics compared with our head camera. So it was very excellent, sir. And coming to, uh, so actually, this is my 30th workshop I attended in NID Warangal. So since I'm attending workshops 2009, so many faculties, internal faculties are explained. But this time, this is 30th workshop I attended with international faculty, Professor Bhaskar Chobe sir. So I'm very much thankful to him. He was explained nicely. And coming to next, Professor Murali sir explained about FPGA's architectures nicely. And on the Saturday, actually, I have 4 classes. I altered everything and came to this for this workshop on that FPGA because openly I am saying that 2000, I think 2019, I attended one more workshop. Professor Murali and Sierra sir organized one workshop. It is related to VLS designing. On that day, sir explained some open sources. That open source I implemented in our college. And I teach my students, and they also publish 3 more papers. A simple software, that is DEET software. DEET software, I implemented in our college, and also I conducted workshop also. So much impressed my head and principal also. And this time, I am confidently saying that now next I am going to conduct an FPGA dumping, how to dump in our college. Surely I am do that. So thank you, sir. Thank you very much. It's my pleasure. Thank you, sir.
Respected dignitaries on the stage and off the stage, and my co-participants, a very good afternoon to everyone. This is the first time I'm attending the course or workshop in NIT Warangal. I felt very happy, and I would like to thank Professor Muralidhar sir, Sriya Rao sir, and Department of NIT Warangal, HOD ma'am, and Dean Srinivas Rao sir for giving me this opportunity. Coming to the course, in this course, we have learned many things. Professor Bhaskar Chobe sir have explained us very well. The way of teaching by the sir was very impressive. We have learned many things. We have learned some, including the course content also. Apart from the course content, I have also learned some teaching techniques. As a teacher, I am from Vagdev Engineering College. I have learned many things from the sir. From the bottom of my heart, I would like to thank once again everyone. Thank you, sir.
Good afternoon, everyone. On stage and off stage. I am Yogita Rajuri from Kaktiya University. So, a part of workshop, we learned a lot. So, first of all, I would like to thank Muralidhar sir for making us to participate in this event. So, from starting day onwards up to till now, we learned a lot. This thinking was and thoughts are so provoking us. And thank you, sir, for helping us. And we have learned a lot. Thank you, sir.
Anyone else who want to share their feedback? Now I would like to invite Dean IIRA Professor S. Srinivas sir to speak few words.
Good afternoon to all. So respected Professor D. Vakula, Head Department of Electronics and Electronics and Communication Engineering, and Professor P. Muralidhar, Coordinator of this 2-week Gian course, and faculty members of ECE department. Here participants came from different institutions. Welcome to valedictory function. I thank all the participants for showing interest to attend this 10-day Gian course by attending physically, and you might have got lot of knowledge by attending the classes handled by the NIT faculty as well as the foreign expert Bhaskar Chaube. So from the course I came to know that there are so many contents were discussed in detail from the fundamentals to advancing. 10-day course is not a simple thing. It can be considered as a almost like a 2-credit course, because number of hours with reference to number of hours as well as foreign expert is available here. You might have interacted beyond the class sessions also. So all of you might have acquired a lot of knowledge. So we all know that in electronics and electronics engineering, mainly you people will deal with transistor. We will study from the fundamentals itself: transistor as a switch, transistor as an amplifier, transistor as an oscillator, transistor as a resistor, transistor as a counter, like that. So those the applications of transistors are increased year by year. Now it has entered into the robotic head also. So many sensing mechanisms also it is taking a major part. So in electronics applications, transistor as well as MOSFET, that is also comes under transistor family. So these devices are very popular. In electrical engineering, we have power devices. So they handle huge amount of power, and whether IGBT or SCR or MCT, mass controlled thyristor, etc. But you are confined to very less number of devices. That is a very good thing, and its applications are many. So that is also an appreciable thing. So nowadays for a signal processing as well as image processing, all these things, so many, not only the transistors, VLIs, part of the VLSI chips, etc. came. For basic thing is only transistor. Now system on chip processors also came. Now on chip sensors also is coming. I came to know from this course content that sensors also coming in the chip. So technology has increased a lot. All of you might have acquired sufficient amount of knowledge. You can refer, all these courses are recorded, and you will have web link. Once again you can listen to those courses, so you can further strengthen your subject knowledge, and email might have shared by the foreign expert. You can also interact with him and try to acquire more and more knowledge. So I thank all of you for showing a lot of interest to register for this course and attending this course. I thank the National Coordinating Institute, IIT Hyderabad, Director IIT Hyderabad, and Dr. Anil Agarwal and his team. They are speeding up of the process of reviewing the proposals received from GAN phase program, and after that sanctioning the money and monitoring the course activities as well as financial activities very closely. My special thanks to IIT Hyderabad director and his team for very closely monitoring as a coordinators at IIT Hyderabad. And another thing is, all of there are so many courses are conducted in GAN phase 4. I already told it during inaugural function, and this department got 6 courses and 5. This is the 5th course ending. One more course is there. That is also a 10-day program. You can see, visit our NIT Warangal website or IIT Hyderabad GAN website. One more course is there in this department. It will be conducted in the month of March. So if you are interested in that topic, you can register or otherwise inform to your friends, classmates or colleagues, or give wide publicity that they also come and attend the course physically. and we came to know that even the people, many of the courses, the participants who are interested to register the courses, they may be looking after the course and they may be postponing. Tomorrow we can register, or day after tomorrow we can register, and most of the courses last 1 or 2 days registrations are increasing. So people are creating some tension to the coordinators with a lot of efforts. They are contacting the foreign faculty and preparing the proposal and submitting, and after a lot of rigorous review process, courses are getting sanctioned. Once brochure was displayed, better you apply well in advance so that the unnecessary tension among the coordinators will reduce. Not only our sanctioned courses of NIT Warangal, any Gian course or Spark course which was sanctioned to any institution, so better apply at the earliest so that the confidence levels of the coordinators well before starting will increase a lot. So I wish you all the best to all the participants. So this is all of you may be in the mood of going home. So don't forget the subject, and if you have any doubt, once again you can listen the courses and contact the faculty coordinator here as well as foreign coordinator also. So continue. These robots are entering in all fields of the engineering. Not only in engineering, medicine field also they are entering. And from the course contents we know that it is imitating the human brain. So how it is working dynamically, like that we are artificially creating with the help of these robots and all. So a lot of knowledge is required, and a lot of patience is also required to do everything in a systematic way. I wish you all the best to all of you. Thank you.
Thank you, sir, for your valuable words. So I invite Professor Sai Prakash sir to give the future course is conducting in March. So that highlights of the course he is going to present. Maybe if you are interested, you can register immediately. Okay, right.
Good afternoon, all of you. Good afternoon, dignitaries on the dais and off the dais, and my dear participants. Actually, I was also trying to attend some of the lectures in this program, and I found it very interesting. And the effort what Professor Muralidhar sir has kept is tremendously high, and the outcome is very good. Like, the lectures are very good, and I think most of you have enjoyed it. And if you try to see the course content, the way they have designed and all, started from the basics to the end, it was quite interesting, and they kept the phase up to the last point. It is not that they have taken it to some point and left it. They have covered almost all the required technology and the platforms, both hardware and software, to the end. And I really appreciate and I thank Professor Muralidhar for that. It is a single-man show, and he has done it alone, right? He has not taken the help of his colleagues also, and it was meticulously planned and it was well executed. So thank you, sir. And coming to the department, there are a lot of opportunities which are there where you can interact with most of the faculty. It is not that it is restricted. You can check from the website, our HOD, our Madam Wakula, or anyone in the department. If you try to contact, they will help you out in case if you have any technical doubts or some problems and all, we'll help you out in solving that, right? So don't assume that or get scared that you cannot contact the department and all. And especially if you try to contact our HOD Madam, Wakula Madam, she'll try to sort out if you have any problems. And coming to administration, we have a very good director, Professor Subudhi, Vijayadhar Subudhi. He is cooperative and he helps us in executing the things in a fashionable manner. And coming to the Gian courses, we have a very good dean, and Professor Srinivasa, and he helps us in getting more courses this time for NIT Warangal. If you try to see the statistics, I think the maximum limit is 50 courses we can apply, and we got almost 25, 50% strike rate. And I think this is the only NIT which has that highest strike rate, I think so. Measure. Right. Thank you. Coming to my program, I have a course on the Gian only, Gian course on aerial networks, which are concentrating on drone networks because within a short span of 1 to 2 years, you will be seeing 8 taxis which will be flying around us, where if you want to go to one place, you can book a, like Uber and Ola, you can book a taxi, 8 taxi. It will come and land up on top of your building where you can sit inside the drone and go to whichever place you want. So looking from that end, as our Prime Minister also Narendra Modi ji has told, we are trying to look more into our Atmanirbhar, like we develop our own technologies in both AI and the drone technologies, where we will be number one in implementing things. So in that respect, we are trying to focus on one more area called as aerial networks. And this is also referred to as, if you try to look into the technological front, we call it as SAGIN networks. It can be space, air, and ground network. They are integrated. So now the way we are trying to look at is to integrate all these technologies, terrestrial and non-terrestrial, and see that the areas where the technology has not entered, like for example, if you try to see the monitoring the forest or monitoring the mountains or some sea and all, we don't have a network over there. But still, in the 6G, we are trying to see to cover all the uncovered areas. So this is next step towards that, where we are connecting the aerial networks. So I think all of you might have got the WhatsApp brochure right now. If you try to look into your WhatsApp group, yeah, a friend has posted that one. So try to pass on the information to your friends. Wherever it is useful, people will try to look into it. Professor is Professor Kamish from UNT, Texas. He is coming down for that lecture. Along with me, we are trying to deliver around 28 lecture hours, where you'll have some hands-on training, where we try to simulate and show you how the trajectories of a drones will be and how the intercontact between the drones will happen and so on. Because when multiple drones are flying, it is not that easy to control them. So they need a inter-drone communication where they coordinate and then they travel, like the aeroplane network and so on. So this is a few idea about what the course conduct is. And with this, I'll thank our Professor Muralidhar for giving me a slot to tell about the program. Thank you all. And I wish you join it. Thank you.
Thank you, sir, for your enlightening words. I would like to invite our beloved HOD, Professor D. Vakla ma'am, to speak a few words.
A very warm good afternoon to all the dignitaries on the dais and the participants, scholars and dear faculty. We can hear from the feedback of the course, like the feedback is very good. We can see participants who are attending 30 courses is not a common thing. Like you can see the attraction of FDPs run at 1080 in and around different places. So you can see the popularity. So I think that popularity maintains still and it continues. And to maintain that popularity, you can see how much effort the faculty are putting so that each course is done, delivered and run effectively and efficiently so the participants get the maximum benefit of the courses. So this is our efforts put by the EC faculty that I can proudly say regarding the department. And regarding the resource persons, I think you can see, we have seen the energetic nature and dynamic nature of Bhaskar Chaubey, Professor Bhaskar Chaubey. And he is the proud alumni of NIT Warangal, also EC department. And regarding him, what I can say is the faculty remember him more. That means that is his knowledge or his intelligence or his hard work he has kept during his academic career, his studenthood at the NIT Warangal. That's what the greatness of the research person. And I wish all the participants do come as frequently as possible to NIT Warangal for any sort of interaction or collaborations or for FDPs. Thank you one and all.
Thank you, ma'am, for your valuable words. Now it's time to distribute the certificates to participants. I request Professor S. Srinivas to distribute certificates. Rania Jainab. Damera Divyasri. Ponakala Jivita. A. Snigdha Priya. Divyasri. Jivita. A. Snigdha Priya. K. Anjali. Shivachendu. A. Shivachendu. A. Shivadanush. K. Nagarani. R. Yogita. L. Sri Pravalika. B. Trisha. M. Shravyashri. B. Srija. Moppidi Rajkumar. T. Pradeep Kumar. మీకు మీరు కూడా మద్ది రాజు, డాక్టర్ భారత సతీష్, డాక్టర్ గన్న కోటేశ్వరరావు, దామినేటి ఉమేష్ చంద్ర, అజయ్ భవిశెట్టి, సంజయ్ ముడు, సంజయ్ మడుపు, బి నాగమణికంఠ, లక్ష్మీకాంతం దుర్గం, Bukke Harishma, G. Sirivennela, Janagam Venkatesh, Chinnam Manasa, Mahesh Tandra, Danala Chaitanya, Daravat Parvati, D. Ranjit, Ajay Kumar Nayak, D. Veeranna, Krishnakant, Gopal Krishna Tota, Vijay Kumar,
Anyone is there still? Registered participants? Not received certificate.
it's time for vote of thanks by Professor P. Muralidhar sir.
Thank you, sir. It is my privilege to propose vote of thanks on this occasion. So first, I extend my sincere gratitude to Professor Vidyadhar Subuddhi, sir, Director NIT Warangal, so for encouragement and vision, and the vision continue to inspire us. A heartfelt thanks to Professor Bhaskar Choube, Chair of the Institute of Analog Circuits and Image Sensors, Gian, Germany, for being part of this academic initiative and enlightened the knowledge on different sensors. I extend my gratitude to Professor S. Srinivasarao, sir, Dean IRA, the local coordinator, Gian program, NIT Warangal, for their unwavering support in making this program a grand success. My special thanks to Professor T. Vakla Madam, Head of the Department EC, NIT Warangal, for her guidance and leadership in organizing this event successfully. My sincere gratitude to the course coordinators, my co-coordinator, P. Srihari Rao sir, for his support and planning and encouragement for conducting of this course. And My special thanks to all attendees for your participation and enthusiasm throughout this course, and also thanks to all the organizing team, organizing the scholars for supporting to conduct this event, and thanks to all the participants and also the sponsoring institutions, the management of the institutions for sponsoring this. Thanks to the Vagdevi Institute Principal, Professor Prasad Rao, and also thanks to Prakash Rao, Principal Vagdevi, Prakash Rao, and also special thanks to Kakati University, what is the faculty name? Mahesh Babu. Mahender for sponsoring the students to attend this course, and also thanks to JNTU principals for sending their students to attend this course, and thanks to all MTech students as well as PhD scholars. Thank you, one and all.
Thank you, sir. Thank you, one and all. Please stand for the national anthem.
जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
I request all the dignitaries and participants to join for a group photograph.
Cheers.